Yeah, welcome to today's edition. My viewers, you are doing well. Some of you are writing comments, some of you are liking my videos. I really want to appreciate you all. I want to also thank professors that have made me who I am today, especially Professor Nelson, my own very professor who supervised me during my projects in those days in school. Professor Ide, you are recognized. And it shows that what Professor M.O. Wonu has taught me is reflected here, because once I get the feedback, it means that the communications I am making or the videos I am making, people are really watching. So I like you all. Please like and subscribe this video so that we can now encourage us to do more of them. So like we have been talking, just briefly I want to highlight it. We've been dealing with capacitor. This word, capacitor. And some of you might be wondering why is he so interested in a capacitor. You don't want to talk about other areas of physics. We are coming to that. Of course, in electronic world, of course, we know that physics is broad, very, very broad. Because physics is so broad, we will just be taking them small by small. But capacitor as a component, it can anywhere you want to talk about, whether in your mobile phone, in your DC circuits, in your computer, gadgets, name them. You must see components called computer capacitor inside of them. So today, and then in the previous videos, we've been able to highlight some equations, differential equations that you can use to solve problems with this capacitor. So, and then we have used graphical solutions. I'm supposed to be doing simulations with some of these graphical signals that we are displaying, especially if we have oscilloscope. But because we don't have oscilloscope here, I don't even have the Simphy. That's a software that we can use, but it's there in my system anyway if you go to the lab. But for today, I'm going to use this marker and this white to explain the following concept. And then today we will outline some things we are going to cover, because we are wrapping up in this before we go into the major design calculations. So number one of the things we are going to look at today is overview of capacitor. Overview of capacitor. Two, we look at arrangement of capacitor. Three, we look at what we call design considerations. Design considerations. Four, we look at applications. Five, we look at energy storage. Energy storage. Okay, so quickly, before we finish that, let's pick this overview to study, just to talk about. So for the overview, I want you to know that capacitor is just a component, it's an electrical component that has terminals. It has terminals, but because some of them are classified depending on what you want to achieve, they are basically categorized into two: the non-polar, the non-polarized, and the polarized. Polarized capacitor. What is the difference? The difference is that in non-polarized, they are not considered the terminals. For instance, if this is a non-polarized, these terminals, if you want to insert it into your circuit board or your circuit design, you don't consider whether this one is positive or negative, or this one is positive or negative. You just insert it because they have been configured like that. Unlike this one, the polarity is stated, and then this has to do with code. They use code to determine the capacitance, the value of the capacitance rating is in code, in what we call numerical code. It is numerical code we use to denote the capacitance of this non-polarized form of capacitors. Whereas in this type, the capacitance value are pasted and labeled on their surface. As you buy them, you can see something like 132 microfarad and so on. So this is the capacitance. And again, you might wonder, what is the difference? The major difference is that in this one, this is used for power supply. Okay, that's why they are called a electrolytic capacitor. But this, they do not have what we call a usage, just small. Again, the ratings for this is basically in picofarad. And for instance, if you have the code, maybe 103, you know, for you to read the code. Remember I told you it's in farad. This is going to be, bring down the first digit, which is 1, bring down the second digit, this is telling you how many zeros. So this is 10,000 farad, the value of that capacitor. So, but in this case, the capacitor is in microfarad or in millifarad. Of course, pico means 10 raised to the power minus 9, okay, or minus 12, which is very small. Okay, while nano is to the power of minus 9, but micro is to the minus 6, and then milli to the minus 10. Okay, so that is the major differences. And then in symbol, this is that two parallel plates. This one is something this way. So we have positive here and then negative the other side. Very bold written. So that is about the resistor. And then what is it made of? Components of these capacitors are mainly the outer coating, which is made of aluminum foil, wrapped to cover these internal layers. What is this internal layers made of? Two dielectrics to separate these metallic plates that the lead terminals are being inserted. That is what these things are made of. And then the lead terminals are all metals, because without them being metals, you cannot discharge them. Of course, you know, when you want to check the measure using a multimeter to know the value of a capacitor, you need to discharge them first by short circuiting. If you bring a metal and put here, especially if the voltage that is inscribed into the capacitor is not that big. If it's big, if you short circuit, it can blow. And that's why you need to be careful while dealing with capacitors. So that is all about the overview of capacitor. And then we move into the second stage. What is the second stage? The second stage is going to talk about the design consideration. What do you mean by design consideration? By design consideration, a designer who wants to design a capacitor should take note of the output and input voltages. The output and input voltages has a very big role to play in your design consideration. Now let's take for instance this circuit that I'm about to draw on the board. Looking at this circuit I'm about to draw on the board. This is a switch. This is a capacitor here. So this is connected to a cell, and this cell has this connected to a load. This load can be a bulb, and then this is the switch. So this switch can flip this way if you are charging, and then if you are charging it now, you see that the current is flowing like this, while this load is not connected to the circuit. But if you now want to discharge, you remove it from the cell. This is cell, the voltage source. This is the capacitor, this is the key or switch. So if you flip it to this side, you begin to use the stored energy here to power this. So now the capacitance value is how much time did it take this thing to dim, and immediately you remove it from the power voltage source. How long did it take it to the light to go off? So if you take a higher number of time, maybe 2 hours for it, now know that the capacitance of that capacitor is very high. Okay, so in your design consideration, you know this is your input source, this is your voltage, output voltage. So you need to consider one, the power rating of what you are going to power with the capacitor. 1, 2, you need to consider this the following. You need to consider the following. One, remember that the capacitance varies directly as what? The dielectric, the permittivity of the dielectric material, which is epsilon. Okay, and capacitance is also directly proportional to the area, the overlapping area, and that's where I'm going to pause a little to discuss on this overlapping area. What do we mean by this overlapping area? Okay, if we say that what we mean by this direct proportion means that if the area is higher, the capacitance goes high, and if the capacitance go high, the dielectric of the material, the permittivity of the dielectric of the material will also go high. So now let's talk quickly on the dielectric, this permittivity. What is this all about? And because you know, in your distance, your elementary electrostatic force equation, that formula says that F is equal to Q1 Q2 all over 4 pi epsilon 0 r squared. This is given to us by Coulomb, and then you now see that there is what we call the permittivity of free space. So this permittivity of free space can be related to this by denoting that the permittivity of a dielectric material, epsilon, is equal to the relative permittivity K, and then multiplied by the permittivity of free space. This constant now is given in value as 8.85 times 10 raised to power minus 12 farad per meter. This is the unit. Okay, if you know this, sometimes the relative permittivity of material, depending on whether it is air, liquid, or gas, or solid. If it is air, it has a value. If it is really solid, it has a value. Sometimes 1, minus, or 0, as the case may be. So when you know that, it will be easier for you to calculate the permittivity of the dielectric material. Okay, so now we have to consider that why do we begin to look at the surface area of overlap while considering the design consideration? Why it is necessary is because, for instance, if, for instance, a material is designed, a capacitor is designed to have this shape, as I'm about to write on the board. Maybe from here to here it's given to be, let's say, 0.5 meter, and from here to here is given to be 1 meter. You can now see it will be difficult for you if this is the material that they use to design the capacitor, and someone is asking you to what's the area of this shape. You can now see that it will pose you a little challenge if you don't know how to deal with the composite shape. This is composite shape because it has more than one shape embedded. If you look at this very well now, you see this is semicircle, and then this one is a rectangle. So how do I do that? You now add the area of the semicircle plus the area of the what? The rectangle. Of course, what is to calculate the area now means area of this shape is what? Area of a semicircle. What's the formula for calculating area of a semicircle? Half pi r squared plus the area of a rectangle is the length multiplied by the width of that. So when you sum these two areas, you get the value of your area, and then you should be able to relate them properly. So if you are designing, you put the shape of the overlapping area into consideration because it has a direct relationship to the capacitance that you are giving to the material in your design. Thank you. Now we are moving over to the next item, and in the next item we said we are going to consider what we call arrangement. So in our arrangement, I will not go into so much, I will not go into derivation. In our arrangement, I want you to know that we have arrangement of capacitor. So in this arrangement, we have two types of arrangement, series arrangement and two parallel arrangements. And you may be wondering, why are we going to arrange these things? Why can't we just build a super capacitor and then use it in what we want to do and then go our way? No. Sometimes you might need 0.1 microfarad and you only have 1 microfarad capacitor. What will you do? As an experienced engineer, what you need to do is to do your addition. For instance, in series arrangement, you know what I mean by series? The end to end, the positive terminal of one device is connected to the negative terminal of the second device. That's what we mean by series. Of course, if you want to now use for instance, capacitor, you see this is negative, this is positive. For instance, you bring this negative of this second capacitor, C2, C1, and connect it to then we give it a voltage source from here. That's what we mean by series arrangement. And then for this, the equivalent capacitance, the effective capacitance is going to be 1 followed by C1 plus 1 followed by C2. This is the formula for calculating the arrangement of capacitors in series, so that, for instance, if you are given 1, for instance, if C1, so if C1 is 1 microfarad, so if you have arranged it like this, it means that the total for this arrangement will be 1 over C total is 1 over 1 plus 1 over 1 all in microfarad. So if you do your mathematical gymnastics, you have 1 over C total is equal to, the LCM is 1, okay? So 1 here, 1 times 1, 1 plus 1, because that will give you 1 over C total is equal to 2 all over 1. So this 2 is, remember they are in microfarad, just like this. If you do this crossing, you have 2C2 equal to 1, so that C total will be 1 over 2 in microfarad. Okay, so that would be the effective will now be 0.5 microfarad. Okay, that is the value for that arrangement. You now see from one individual capacitors of microfarad, we're able to get 0.5. We cannot get it in the market, but we have used our brain to know that what will give us the voltage output we need is by the time we now arrange this thing in series. So now, let's also look at the parallel arrangement. It's the exact opposite of this arrangement. We take it and play. So in parallel arrangement, you have this capacitor connected to this capacitor in this way. So we are giving them to the same source. This is C1, this is C2. You see that at this point, one charge is flowing, current is going to the voltage source is from here. So you see that at the end of the day, you have that the effective capacitance is equal to C1 plus C2. It's just to add them to, so that if C1 is 1 microfarad and C2 is also 1 microfarad, the CEF total, when you arrange it in parallel arrangement, will give you 1 microfarad plus 1 microfarad. If you add 1 microfarad to 1 microfarad, this CF, it will become 2 microfarad. You see that in parallel arrangement, the effective capacitance is larger than when you do series arrangement. Clear? So this is what it is here. So now that we have finished talking about arrangement, so it is your choice to know either to arrange your capacitors in parallel or in series, so that you achieve whatever result you want to achieve. The same way we arrange resistors and other electrical components in these directions is the same way we do in capacitor. They are not different. Thank you. So now we are going into what we call into the next item, which is called the application. So application of capacitor, or what we call where we use our capacitors. So what question do we need to ask ourselves? Why do we disturb ourselves with capacitor? What is the main function of this capacitor? One, we use this capacitor in the connections of induction coils, or what we call induction motors, electric motors, water pumps. For them to pump those fluid within that pressure, some of them that comes with single phase, you need to carry a very super capacitor to help in the connection, to boost the RPM, the revolution per minute, or what we call the speed of the motor. So in that case, if you finish your arrangement, your coiling, you have finished your winding, you must have to assist that starting winding and the running winding by using the capacitor. Most of the time, that's the major application of that. And then in the ones we can demonstrate even with the marker and board, even the other one we can still demonstrate. But let's pick this one. And so I say it helps to balance the RPM of single phase electric induction motors. So so one we have said it helps in balancing the RPM of single phase electric induction motors by normalizing the starting winding. Two, the second application of this thing is to do what we call filtering. Filtering is a big word, but we are going to try as much as we can to simplify that word, just that ambiguous word. That's filtering means that most gadgets, just like your mobile phone, your televisions, radio, name them, they do not, your drones, they do not use direct AC generated signals. If you have AC generated signals, the signals can go this way. The signals can go this way. Your AC generated signals can always go this way. This is your wave. These things goes this way. You see them wobbling up and down. That shows that if you use this thing to your gadget, there will be a time where to have the maximum. Remember, the current and voltage are moving in the same way because it's AC, periodically function that move like this. You can't use them to operate your normal mobile phones and all that. So for you to do this filtering, you must have a system what we call a power supply that can do what we call converter, to convert AC signals to DC signals. And then what do we mean by DC signal? This is AC signal coming. If you put it in a DC, you now have that the DC will cut off this negative functions. If you cut off these things, then you begin to have these signals coming. This is DC, but because this thing can also have a place where you have signal, it will not be smooth. So to smoothen this, to filter it, to remove the unwanted signals, to smoothen this, we use an AC. We use a capacitor to do that job. And then let me take a very simple, because we look at a very simple circuit. What we are saying here is that if you have your AC coming from AC source and you pass it to this type of circuit, let me use a full bridge rectification. Okay, if you have this, remember your diodes are connected this way. So this AC source is going to come this way, connect itself here. So you get to this point. So for you to get this, your VA, your input voltage is coming from the AC. Of course, the transformer will do its own job to push up or to push down. Transformer has done its job, and this is picking it for rectification. So when you come here, you can tap from here, move into the load. So we can take this as our load resistor. This load resistor can be anything, electric motor or anything motor power. So now this load will do just one single thing. If what you have here, you connect a capacitor, because at this stage you are having this. But when you now put the capacitor, depending on the capacitors, make this thing to move this way, to move in straight line. And this is what we say used for your mobile phone and all that. A smooth signal, direct current signal. So to move this thing from here to here, you see the role the capacitor has played. If the capacitor you have is small in value, and maybe you can still step this thing down using a resistor here. Bring it down a bit so that it can be useful to the capacitor to smoothen the output voltage. Okay? And the output voltage V out come out from there. So that is the major function of the capacitor. You see, it helps to smoothen the output voltage of the watt of the AC current that is coming from the other side, so that you have a seamless transmission. Okay, and then we could have demonstrated it using oscilloscope or a simple Simulink. If you have Simulink or the Simphy app physics software in my system, I will show you how to do that, maybe when we get a projector. Okay, so this is the few things we can talk about. And then finally, for us to look at the other functions, the other items we talk about, which is the storage, energy storage. Before we go into calculations, the energy storage. What do we mean by energy storage? Energy storage. Energy storage. Okay? So if we talk about energy storage, I want you to pay attention, because we cannot talk about energy. What is energy? Say the capacity to do work. The capacity to do work. Energy is required to do work. Now, what is work? In work, in physics, you must have two basic things. The force, which in this case, electrostatic force. Okay? And according to Coulomb says that electrostatic force is Q or Q2 all over 4 pi epsilon 0 r squared. I think we've written this before. This force is what is embedded inside the atom that makes proton and electron to be balanced, so that the world as we live it will not collapse. So using these static charges that we are talking about, of course, you know, if you put a point charge, the proton radiates its lines of force outwardly. These protons radiate their lines of force outwardly to various but the lines of force, you know, one of the properties of lines of force, it must be a straight line. So these lines of force radiating outwardly can be collected, and this field now, that is you are seeing there, this field, which is a region that this influence has been experienced, this field can be used to do work. It can be constructive work or destructive work. And that's what happens when we say we have what we call a repulsive force and force of attraction. Electrostatic force of attraction is when there are like charges, and then maybe neutron and proton. And like charges will repel. That is what we call the force of repulsion. Now that we are dealing with the capacitor, of course, you know, the charges is between negative, so it's purely attractive force, and that's when we now say what work can be done. Of course, you know that if you have the plates, they are separated within a distance, as I've mentioned before. They are separated within a distance, So this positive charge is here. There is a work you need to do to move an electron from here to the other point to dislodge it. Remember, this will move through a wire to come. So that work can be derived. And that work can be derived. If you say the work can be derived, the little work that is done by the charge, a unit charge, is equal to V. Let's say this is equation 1. Okay? And then you recall. Our V is the same thing as saying, because we have Q to be CV, so that V will become Q all over C. So V is Q. Let me be using this small charge for that all over C. Okay? That's V. So we can call this equation 2. So plug equation 2 into equation 1. If I put equation 2 into equation 1, what I will have will be very beautiful. And that will give me this little work that is done by this electric charge. The Q is equal to Q all over C. Okay, this is equation 3. And then if I play with equation 3 by doing my mathematical gymnastics, I have the Q equal to Q all over C dq. Okay, so from here, if I integrate both sides, you now have the U, what we call stored energy. That, if you summarize, the integration means summing. If you sum the whole work, those small work that you are doing, it will give that energy, which we call the stored energy in the system. And what will you do if you do this?